Teardown time. This is a Philips HUE LED light bulb. What's special about this unit is that it's actually reasonably priced, about $15. Cheap enough actually that I can justify tearing it down. The bulbs previous to that were just so expensive. Let's see how they achieve the $15 price tag on this bulb, whether that's through taking a smaller margin or if they've gotten more clever in their technology where they can actually cost reduce it. Let's see how it's built. Well, there's just a multi-page instruction manual on how to use a light bulb. I guess it's one of the challenges with protocols like Zigbee. They seem to have just lots of instructions. Not bad for people who love technology and love fiddling with things, but I wonder it would really sort of turn off the general market. No matter, since I actually love technology, let's look at the bulb here. It's got a metal base and a plastic top. It doesn't look like it comes apart with any sort of hand pressure, so I will have to saw it apart and see what's inside it. So the top's off, obviously, and the construction looks fairly good. It's sort of a metal base here, so it gives the heat from the LED someplace to go. And obviously the outstanding characteristic is there's a circuit board sticking through the emitter array, and it looks like it has an antenna type structure pointing out here. And of course that makes sense, since the Zigbee signal has to make contact somehow, and you can't have it inside essentially a Faraday chamber, which is the bottom here. So let's pop the top off and take a look at this circuit board. So actually, just before I open the top up, I was taking a real close look at the two leads here. They're obviously hand soldered because you can see some flux residue, which they didn't bother cleaning off. But the red lead is especially poor. It actually isn't even on the pad. Essentially, the solder is holding on one side of the pad, and then it bridges out to the wire, sort of hanging in free space. From a workmanship rule, that is just absolutely dreadful. So a very poor quality control going on here. So the emitter cap, I just pried it off. It sort of fits in with a friction fit onto the base here. The black material, of course, is potting compound. It's put there to reduce noise if there's any inductors or capacitors with magneto restriction, which can create sound. The potting compound helps there. It also helps with spreading the heat out and resulting in a longer life assembly. Let's peel that stuff off and see if we can see what the circuit board looks like. Okay, so this is the top view of the circuit board extracted from the potting compound. Let's zoom into the largest component on the top, and that's the controller, which has the Zigbee interface. Much more reasonable computing power here compared to that Cree bulb I tore down previously on this channel. This is an Atmel processor. It's an 8-bit AVR. Here's the data sheet for it. It's a ATmega 2564, and this is actually the same processor they use on Arduinos. However, made it to the processor is a block you might expect, which is a Zigbee. Let's just look at this data sheet here. So we can see the ARM in the middle, and of course, we just zoom out a bit, we can see all the peripherals like the JTAG and the ADDs and the AES encryption engines and all sorts of core functionality. But most importantly, as we carry on to the right, the radio transceiver, a 2.4 gig transceiver, which of course would be just super for doing a Zigbee implementation. So here I see a much more reasonable amount of compute power. That last one I tore down with the Cortex M processor was pretty wild. While we're on the top of the board, let's go to the bottom, and we can sort of see the classic bits, the fuse in the bottom there. That's good from a safety perspective. The fuse, pardon me. The next part up is a choke, basically for EMI. A big transformer in the middle. It's probably, of course, an AC to DC converter, and it's probably an isolated design. I haven't really traced it in too much depth. A Bluetooth bulb, unlike a normal bulb, has to have two power supplies. One that's always on to power up all the Zigbee stuff, waiting for a command, and of course the other one powered up to light the actual LEDs. And hopefully there's two here, because otherwise you end up wasting a lot of power. So looking at the back of the board, let's go to the bottom. That's a full wave rectifier. As you might expect, the AC gets converted quickly into DC. The actual SOIC there is a fairly complete controller. It's from ST. It's known as the HV LED. It is a isolated design. Let me just pop up the block diagram for how to use it. You can sort of see a transformer in the recommended circuit. It is actually designed for fairly high wattage applications, 15 watts, which is interesting. So a fairly comprehensive and integrated controller. The one part above it is another big surprise. It's a 4 megabit EEPROM, just like the Cree bulb I turned down, which had also an SPI 4 meg part. I don't know what's going on here. Maybe Zigbee has some sort of crazy requirement for massive storage tables or something, but here again I see a 4 megabit EEPROM, which is a tremendous amount of storage space. So maybe all talking towards the fact that Zigbee isn't a super compute efficient protocol. Okay, otherwise circuit board looks like it's a standard 2-layer assembly, and it has on the other side here some markings as to when it was built. It was built in the 30th week of 2015, so pretty slow sell-through. I bought this bulb coming into May here now, 2016, so it's been sitting on the shelf for a fair bit, so not a real high selling part. I guess it's not too surprising, kind of getting to some really specialty lighting here. So unfortunately, continuing with the theme of poor solder quality, this component here is a through-hole capacitor, but if you look at this here on this side, let me just set in a picture. What you're seeing there is the solder hasn't wicked through the via and then up into the other pad, so it's a very weak solder joint. In most high-rel worlds, that would of course be rejected summarily, and then right next to it, the wires that went somewhere have the same problem. So very discouraging, actually. It's very poor quality soldering on this assembly, and these are the sort of things that can lead to premature failures of electronics. Well, there we go. So this is Cree's approach to their most cost-effective design. I think they're probably skimping on assembly quality. Those are just dreadful hand solders, and maybe that's how they're driving costs low to going to a shop which has some pretty marginal quality control. A bit disappointing. I mean, it's not much of a bulb, obviously, but that's not going to help with its service life. The Zigbee controller, much more plausible than the Cree one, which used that crazy M0 processor. An 8-bit processor is more like what you'd expect on such a low-cost product, but still associated with it is that 4 megabit EEPROM, so I don't know if there's something going on in the Zigbee protocol that requires some sort of crazy, massive storage component for the protocol to work correctly, but that's a whack of cash for a consumer-grade bulb that does nothing but turn itself on and off. So that was the Philips HUE bulb, the cheapest one I've seen so far.